there will be no glassware cleaning at the start of the lab period next week. It has to be ready to go before you come to lab next week. When you come to lab next week, you're going to be putting all this glassware immediately into the oven, okay? So there is no time for cleaning, so it has to be taken care of this week. So you need your 3-neck round bottom flask, clean and dry. And this, some of you have a 250, some of you have a 500 mil, it doesn't matter. You want to put your 1-inch stir bar in the flask. You want your Liebig condenser ready to go. The Liebig, remember, is the wider condenser, the one with the bigger jacket on it. And you have to dry out the actual jacket too. So we will show you how to do that in lab this week, okay? But you actually need to, where the water goes through, that has to be dry too, because we can't have the water going into the oven next week. You need your separatory funnel ready to go, minus the Teflon pieces, okay? We don't put those in the oven. The stir bar can go, but the Teflon pieces of the separatory funnel cannot go. They will melt. And then it's a good idea to have your glass stoppers clean and ready to go too. We'll take care of those. We'll use those next week, okay? So in a little bit, I'll talk about the second reaction you're going to do this week. Involves an hour-long reflux. That is a really good time to get your glassware together. So for that reflux, I would use your smaller condenser so that you can be getting your Liebig condenser all put together and cleaned out and dried out, okay? We'll go through this list again in lab this week, but make sure that you have all of this clean, dry, ready to go. Again, there's no glassware cleaning at the start of lab next week. So if you don't clean it this week, what you've got is going in the oven, all right? It does have to be dry. So if it's not dry, if there's visible water in there, it can't go in the oven next week. So that's why it has to be taken care of. So you want to wash it, soap and water, rinse it well with acetone so that it can be airing out over the week, ready to go for next week. The other thing you can do is put your initials on it in Sharpie because we'll be calling initials out as we pull things out of the oven next week to get you your glassware back, okay? All right, for experiment 7, we are going to look at step 2 reaction. So let me remind you again what that reaction is here. I'll go through this mechanism here in a little bit, but just as a reminder what reaction we're talking about. We're talking about bromoethylbenzene reacting with quinoline to form styrene, okay? Now you guys have not covered this yet, but you will very, very soon. This is known as an E2 elimination. So you will talk about substitution and elimination mechanisms in lecture here very quickly. You can also name this as a beta or a 1,2 elimination. And this mechanism, elimination mechanism, we talked about last week is we're looking at a dehydrohalogenation of that bromoethylbenzene, okay? So we're losing a hydrogen, a proton, and a halogen from the whole process, okay? When we talk about an E2 elimination, that means that it happens in one step and there's no intermediate that is formed. Okay, and again, you'll get into more detail of that when you talk about these type of mechanisms in lecture. But as far as the actual reaction, we've got our bromolethylbenzene. You're going to be heating it in quinoline. Our quinoline is our base, and I'm going to talk about why we use quinoline here in a minute. So our quinoline is our base. It will take this proton, the electrons then flow here to this carbon and up, and then we lose our bromine as a process, so as a result of everything. So we've got here this double bond that is formed from the elimination of the proton and our halogen. We form our double bond here of our styrene, okay? And then we also make this quinolinium salt that's counterion is a Br minus, all right? So this all happens in one step, and there is not an intermediate involved in the process. In a couple weeks we'll talk about another elimination where we actually do form an intermediate in the middle there. Now, why do we use quinoline instead of just any other possible base there, okay? First of all, this is a good non-nucleophilic base. Now, our other possibility would be a nucleophilic base, like KOH, NaOH, something like that. The problem with that is, instead of getting elimination, what we could get is instead a substitution reaction, okay? And so we could substitute that bromine with an OH group, and we don't want that. We want this elimination reaction. So that's why we're not using something that is nucleophilic. So we're using a non-nucleophilic base. It can't act as a nucleophile. It can still act as a base, but not as a nucleophile. Now, another example of that is pyridine, but we're not using pyridine. The reason for that, we need a boiling point that is really high. So the boiling point of quinoline is about 237 degrees. The boiling point of pyridine is about 115 degrees. This is not a high enough boiling point to distill over our styrene, and so that's why we can't use the pyridine. You have to use something that has a higher boiling point than the styrene that we're trying to distill away from it as the product, okay? And so that's why we are using quinoline in this experiment, all right? Now with the quinoline, you do need to be really careful with it. You want to handle it with gloves. It really has a strong stench. You don't want to get it on yourself, so keep it in the hood. In the reagent hoods is where the quinoline is. There is a pipette there that you can use to draw up. You need 10 milliliters. If you draw up 10 milliliters to the line where it says 10 and then just transfer it to your graduated cylinder, you will get the 10 milliliters, okay? So you want to be really careful handling it, not to spill it, not to drip it everywhere. Take your graduated cylinder straight to the reagent hood to get it, and then put a piece of saran wrap over your graduated cylinder too, so as you're taking it back to your hood, we don't have the strong stench of quinoline throughout the lab as well, okay? So for that reaction, what you're going to do is, as you heat the reaction, it takes place. And what we're going to do is then do this all in your all-in-one simple distillation apparatus. So then as you heat it, we're going to heat it high enough that we actually distill off the styrene as it's being produced. But before that, you're also going to collect hexane. So that's going to be your low boiling fraction, is whatever hexane you had remaining on your product from last week is still there. You're going to remove that first before you actually start collecting your styrene, okay? The hexane, you want to get the volume of this because you're going to use that to subtract from your volume from last week to figure out exactly how much of your bromoethylbenzene you actually made, okay? So that's why last week you got both the mass and the volume, because once you collect this hexane, you'll use that volume to figure out how much was bromoethylbenzene versus how much was actually hexane, all right? So don't forget this piece of information. Don't forget to collect this piece of information, and don't forget you have collected this piece of information when you go to figure out yield for your bromoethylbenzene, all right? Now the styrene, we want to collect over a boiling point of 120 to 160 degrees, okay? So that, over that range, whatever you collect, we're going to call that our styrene. If you get to 160 degrees and you haven't really collected anything, that's fine. We're not going to collect anything beyond that. We're only collecting styrene between 120 and 160, okay? So no matter what actual yield you get from this, that's okay. We have extra styrene if people need it to actually boost how much they have to go into the third reaction, okay? But make sure that you record how much styrene you do collect over that boiling point range, because you need that for calculating your yield of your styrene, right? Then after 160 degrees, you're going to stop the distillation, okay? So don't let it just keep climbing. Stop the distillation, turn off the heat, and you're going to very slightly cool your apparatus, all right? What we need to do is we need to get that quinoline mixture out of there before it can become this hard glass if we let it cool down all the way to room temperature. And then you can't clean your apparatus is useless. You can't clean it out, okay? So we need to get it out of there while it's still hot. So you're gonna just let things cool very slightly. You're going to pour the contents very carefully into your organic waste container. So we've made sure the organic waste containers are empty. You're going to carefully pour the contents into your organic waste container. And then you want to have some toluene. So there's toluene in red cans for the next reaction. You want to have about 10 mils or so of toluene available after you've poured your contents very carefully into your waste container. So you're going to use your hot pad, have gloves on, go very carefully. Then you're going to very carefully, because that glassware is still warm, add toluene to it, rinse the contents with the toluene, and pour that into the organic waste container, okay? And then after that, you should be able to clean it with soap and water, and then rinse it with acetone and get the whole contents, the whole apparatus clean, okay? So just don't forget that after you're done with this reaction, you have to clean the apparatus right away, all right? But be careful because it's hot. So you need to be very careful with that, okay? So make sure before your distillation is done, you already have your toluene there ready to go. You don't want to have to go get it. You want to have it ready to go so you can let things cool slightly so that you can handle it with your hot pad, and then dump the contents into the organic waste, and then rinse well with toluene and dump that into the organic waste, all right? Questions with that? Yeah. All right, just be the key is to be very, very careful with it, all right? Okay. So then we have our styrene, all right? You need to know the mass of your styrene, all right? So do the cleaning first, then worry about this part. Then you are going to have your styrene in your 50 ml round of bottom flask that you're going to use for the next reaction, okay? Once you know the mass of that styrene, you're going to go see your lab prof, and they will give you a little bit of styrene depending on what your mass was, okay? So get the mass of it, get it into your round bottom flask, and then see your lab prof, okay? And we will add more styrene to it. What you need to keep track of in your notebook is how much was your styrene and how much was what you got from your lab prof. So you have to weigh this again to know how much you got of extra styrene. You need to know both yours and how much you were given, okay? For the third reaction, you're going to total those two amounts so you know how much styrene you're starting with. For the second reaction, you need to know how much of your styrene you have for calculating yield, okay? Then you're going to go ahead and finish, once you have the masses figured out, you're going to finish setting up the reaction. You're using AIBN for this reaction, and you only use 0.03 grams. That's 30 milligrams, okay? So AIBN, 0.03 grams, all right? You don't use more than that, all right? If you use more than that, you're going to make your polymer chains really short. So the way this reaction works is we've got our AIBN, okay? We add heat to that. That becomes radical. So here is our radical initiator for this reaction. That's what the AIBN is our radical initiator, all right? And you may see some bubbling. You're getting some nitrogen gas that is coming off from that reaction, okay? So then your AIBN then reacts with your styrene, and it forms a radical that then can keep reacting with more chains, more monomers of styrene, okay? The more AIBN you have, the more of these polystyrenes you've created, the smaller those chains are, all right? So the less AIBN you have, the bigger polymer chains you are making, the better off you're going to be as far as collecting your polymer at the end. And I'll talk about the reason why here in a little bit, okay? So you really have to be careful. You're only using 0.03 grams of the AIBN. Now, the AIBN, when it reacts here with the double bond, at the double bond of the styrene. What carbon is that radical on that's formed? Which carbon is that? What position is that? The benzylic, right? So just like last week where that benzylic radical is what is stabilized, again, this week we form that benzylic radical, okay? So that benzylic position is key. We do not form the radical on this carbon. We form it at the benzylic position. So each time it reacts with a new styrene, you're always forming a benzylic radical, all right? And so eventually, after it's reacted with all the styrene that's available, you'll have your polystyrene that has n amount of chains or monomers on it, okay? And you're going to calculate about how much repeat units you have. That's what that n is how many times that styrene is repeating, okay? Now, after this reaction, okay, you're still going to have everything in solution. So the way this works is with the toluene, you have any monomer that's left and polymer is soluble in the toluene, okay? All right? So in the toluene, when you're done with the reaction, you're going to have a complete solution. All of the possible variations of styrene and polystyrene are all soluble in toluene. In methanol, your monomer, so your styrene, and small chain polymer is soluble. Large chain polymer is not. And so This is where the using too much AIBN comes into play. If you use too much AIBN, you're not going to have very much large chain polymer. You're only going to have a lot of small chain polymer. So when you try and precipitate out your polymer with the methanol, which is why you're using the methanol, you're not going to get much of your polymer to precipitate out, okay? So you make sure, that's why it's really key. You have to use the right amount of AIBN, or when you get to this part, you're going to be stuck. You're not going to have any polymer or polystyrene product to isolate. All right. And so here we're using a selective precipitation to get our larger chain polymer of our polystyrene to actually precipitate out of the methanol. Right. Now, when you are doing this precipitation, you're going to have 150 milliliters of methanol in a beaker, stirring very rapidly, okay? You want to slowly add your polystyrene mixture, the reaction mixture that's in the toluene, slowly add that, okay? Because what you want to do is eventually form nice flaky polystyrene. If you dump it all in at once, as that polystyrene is precipitating, it's going to end up precipitating with a lot of toluene stuck to it, and you get these globs that do not filter very well at all, and so you'll be filtering forever trying to get the solid filtered out. So you want to add this slowly to the methanol so you get it to precipitate as it's being added versus dump it all in at once, all right? And we've waited, with this whole mixture, we've waited until it cooled to room temperature to even be adding it to the methanol. Then you're going to keep stirring very rapidly for, I think your lab manual says like 15 minutes. You're going to just keep really stirring it really rapidly, all right? Then turn off the stirring, let it settle, and then you will filter it like you normally would with vacuum filtration. But if you can kind of let it settle a little bit, you can kind of decant your solid too, gets a lot of that liquid off first, and then your solid will start going into the Buchner funnel with vacuum filtration to get that solid filtered out. If you either end up with a lot of globby polystyrene, or you chuck it all in the Buchner funnel all at once, you're probably going to have trouble with your filtering. So it's really important to be careful with how you form that polystyrene precipitate, and then be careful with the filtering so that you don't end up with this mess that just doesn't filter very well, and like we probably even send you away to go to lunch and come back and actually then prep your sample because it is such a mess, okay? So you've got to be really careful with the precipitation. You getting out of lab in a decent amount of time versus standing there forever waiting for something to filter, all of this is really key to that situation, all right? Now, in general, the lab itself actually is pretty time-consuming as well. And next week, like this lab and next week's lab are both, plan on the 5 hours. They will take that whole block of time. So you definitely don't want anything slowing you down in the filtering stage, all right? Remember with your yields, remember parts 1 and 2, you're calculating a theoretical yield. And a percent yield. Remember with this experiment, you're calculating a percent recovery. So you're taking your grams polystyrene divided by grams of styrene to get your yield, okay? This is also known as a weight percent yield, all right? So keep this in mind for when you're preparing your report and doing all your calculations. Parts 1 and 2 are kind of the traditional method of figuring out a yield. Part 3, you're taking grams of styrene divided by grams of styrene. So that's why it's really important you know how much total went into that reaction, okay? All right. For characterization, we've got 3 steps we need to worry about, okay? So our products that we characterize. Part 1, last week, what are the methods you use for characterizing your bromomethylbenzene? You have the silver nitrate test, right? And what else? The density test. That is how you calculated your bromoethylbenzene. Okay, for part 2, the only thing we really calculate or record is that boiling point range for your styrene. So that is how you calculate or characterize your styrene, is over that boiling point range. All right. For 3, you're going to collect an IR spectrum. So we taught you in experiment 6 how to collect that. With experiment 7, you're now collecting it of a solid. So if you remember collecting your experiment 6 unknowns spectrum, remember the background, the anvil was up. That's the same for polystyrene. For the solid actual sample spectrum, you're going to put the little bit of solid on the IR and then put the anvil down to collect the spectrum. Okay. Otherwise, the same procedure that you use for experiment 6 is the same procedure as this. Okay. Be careful. Kind of sweep up the polystyrene when you're done, and sweep it off the IR before you go to like full-fledged clean it. You have to clean it with THF. Acetone will not be sufficient. So there's THF by the IRs for you to use to clean the IRs themselves. Okay, so you're still using a piece of toilet paper, and now whatever residue is left, make sure you also clean the anvil too. So you gotta clean the top and the bottom with the THF, all right? The other thing that we're going to use, so we've got IR spectrum, we're also going to collect GPC data for your polystyrene. So I'll talk about GPC here in a minute and what's involved with that. There are instructions in your lab manual for that. Make sure you follow the instructions, okay, for that sample prep. Part of that sample prep, after you dissolve things in THF, so there's THF in the hoods that say for GPC's sample prep, use that THF versus the THF by the IRs is not as clean, okay? So use the proper THF for preparing the sample. THF is key here, and also we are going to have to filter this, okay? And so in order to do that, you should see your TA or instructor for getting it into the GPC lab, okay? Because we have to, whoops, can't spell today. We have to make sure that we use a syringe filter all the particles out before we prep that sample, okay? On the sample, you should label, so there's a file we'll show you for prepping. You need to label it with initials and notebook page, just like you did with your IR spectrum, okay? And not anything else. So not drawer number, anything else, okay? So for example, I had a sample that was on page 65 of my notebook is where I wrote down the sample prep. This would be my sample ID, my initials and my notebook page, okay? And that is it. In the labs, there is a tray that you're going to put your samples in by your drawer number, and then there's also a piece of paper that you fill out where you put your name and what your sample ID is. Make sure you fill out that piece of paper correctly, because that is what is used to put all your information in the computer for the GPC. I can't read it or we can't figure it out, you may get a funny sample ID because we couldn't figure out what this was. Okay, so make sure you fill that out completely and carefully, and then you'll submit your GPC vial before you leave lab this week. We need that sample because as soon as the lab section's over, we're actually going to start the samples. So make sure you have that before you leave. If you don't have time for the IR spectrum or you don't think it's quite dry enough, you may come into open lab to collect that. But we have to have your GPC sample before you leave lab this week. Okay? All right. So GPC. What are we even talking about with that? It is known as gel permeation chromatography. Another name it's commonly called by is size exclusion chromatography. Okay, so when we're talking about chromatography, and this is the first of multiple we're going to use this semester, chromatography means separation. That is what is involved with chromatography. Okay, so we're somehow separating components out when we're talking about chromatography. What happens with gel permeation chromatography is as your sample goes through the column, there's all this polymer itself actually in the column. And your sample is trying to travel through all of this polymer, okay? And so it's kind of like, if you think about like an English muffin, like the nooks and crannies in an English muffin, all right? Small polymers will sample all of the nooks and crannies, okay? So they will travel through all of the spaces to get out of the column. What that means is they elute or come off the column later because they're taking so much time going through all of that column, okay? Bigger polymers or bigger compounds, and it doesn't have to just be polymers, this can be compounds, okay? But usually it's used with polymers. They are so big, they can't make it through, okay? So they elute sooner because they're not sampling everything. So what that means is when you're looking at your data for GPC data, your big stuff comes off first, your smaller stuff comes off next, okay? Because the big stuff just kind of shoots through the fastest, widest avenue, gets out of there. The smaller stuff meanders through the whole column, all right? With gel permeation chromatography, so that's how we can tell we're using this to determine size of the compound, all right? That's why size exclusion chromatography is another name for it, is we're trying to figure out the size, and the separation is by size of compound. Besides how we are trying to separate things out, with chromatography we always have a stationary phase and a mobile phase. Our stationary phase is the column and the polymer on the column, okay? So that doesn't move, it moves through it, but it's stationary. It's not flowing, it's just staying in one spot. The mobile phase is the solvent, which is THF, in this case, that we use to push the sample through that column. So that's what's moving, is the solvent is moving through the column, all right? And so what happens as it's separating, we've got here kind of a schematic of our system here, okay? So we have our sample tray, that's where we put all our vials, then there's some automation that takes the sample, injects it into the system, and we've got solvent, in our case THF, pumping through the system. We go through this column, which also usually is in an oven. That's our stationary phase that it goes through, and it's separated, so when it comes out on the other side, it's actually separated. And then it's somehow detected. In our case, it's a refractive index detector. And then that information is sent to the computer, okay? And then we process our data. When you have polymer that's all unique, discrete sizes, you would see, okay, like in this case, A is 171,000 grams per mole, all right? So it's coming off sooner versus the 28,500 versus 2960 versus 106, which would be the styrene, okay? These are all discrete sizes of polymer. It's really hard to actually do that. You have to use a really controlled system to be able to do that. We're not going to do that, okay? And I'll talk about what PDI means in a minute, but when you have a discrete type of polymer, it has a PDI of 1. What we're looking at is more a system where we've got, all sorts of different size polymer coming off, and it's all kind of out of one big sample. So our bigger stuff into our smaller stuff, and what actually ends up happening is it just looks like kind of this big mound of sample that comes off. It looks like one big hill, okay? Because it all is coming together. So it's more like this kind of thing here instead of discrete peaks that you can actually see, all right? Now, on here, it talks about you've got an MN and an MW, so I need to define what those are for you. So MN is a way to determine the molecular weight as well as MW for that polymer. MN is just an average molecular weight. It's a simple mean where you basically add everything up and everything is divided by the total and it's all counted the same, okay? So it's a number average molecular weight. So this is a molecular weight is what is being calculated, but all the polymer strands are counted equally with an MN, okay? An MW is a weighted average, okay? And so this is going to be your weighted average molecular weight. In this case, the heavier polymer is going to be counted greater than the smaller polymer, okay? So I'm going to show you a couple examples. But this is known as the weight versus number average. This is going to be our weight average molecular weight, okay? So I'm going to take the example that's in your lab manual, where it's looking at the weights of football players, okay? So the number of players and what they weigh. Okay, so we've got this distribution. So we've got one that's 150, another that's 180, or two that are 180, one that's 210, and two that are 250, okay? And I'm going to show you how to calculate both with MN versus MW. Okay, so MN, we would just take all of the weights and divide them by 6, all right? So we take 150 plus 180 plus 180 plus 210 plus 250 plus 250. Okay, there's all 6. Divide by 6. Everything is counted equally. The total is 1,220. Divide that by 6, we come up with a number of Mn is 203. So if we count all those weights equally, the average size of the football players is 203, okay, 203 pounds. Another way of looking at it is you could take 1/6 times 150 plus 1/6 times 180, so on and so forth, okay? Same thing, but everything is counted equally. With MW, the bigger players are counted more, or the bigger polymers are counted more than the smaller ones. So what you do is you take the mass, the molecular weight, divided by the total. So 150 divided by 1220 times that molecular weight. Plus, then we'll consider our 180s. 180 divided by 1220 times 180. So as we get bigger, this becomes a bigger number all along the way. So things are getting, the bigger the number, the bigger things are being counted. So we get to our 210. And then plus our 250s. So you guys should understand how to make both of these calculations. So if we go through all that math, what we get here is 210. So it's a bigger number because the bigger weights were counted more in the average, all right? So in general, MW is either going to be greater or equal to MN, all right? MN is not going to be bigger than MW, just because the way it's calculated, okay? So if it's equal, then you get things like those discrete peaks in the GPC because they are one molecular weight, all right? We have a way of measuring this. It's called polydispersity, which is the PDI, and that is calculated by calculating the MW over the MN, okay? And this is either equal to 1 or it is greater if MW is greater, okay? If it is equal to 1, then you say that your sample is monodisperse. If MW and MN are equal to each other, that means there is only one molecular weight in that sample and it's monodisperse, okay? So if you've got a PDI of 1, it's monodisperse. Anything else beyond 1, greater than 1, so if your PDI is greater than 1, it's known as polydisperse. So when you get your GPC data, you're going to be looking for what is MN, what is MW, and what is the polydispersity. If you don't have your polydispersity, you can calculate it from your MW and your MN. But that's the 3 pieces that you're going to be looking for on that GPC data. There's going to be a whole lot of other information on there. You want your PDI, your MW, and your MN. That is what is most important. Okay? All right. As far as, so the GPC data, we will run the samples and then we will get you back that data. There won't really be like a standard to compare it to or anything like that. You're just looking at your own data and what information you get out of there. Remember that MN and MW are molecular weights. So when we go back to calculating the repeat units on your polymer, what would you use to figure that out? What information would you use from your GPC data? their molecular weights of your entire polymer, right? And you know how much A styrene weighs, right?
Yeah.
So if you take your molecular weight divided by A styrene, you'll figure out what your repeat units are, right? Or roughly, pretty closely. What would be a better number to use, MN or MW? MW, as far as polymer information, is considered to be a more valid representation of the polymer. So when you do that, you should use MW for that calculation. Okay. The other thing for data analysis, I am going to post on Moodle a standard IR spectrum for you to compare your IR information to, okay? So when you collect your IR spectrum, instead of going out to the literature and looking for polystyrene, there is a spectrum that I will post on Moodle, and you're going to compare your information to that. You do not need to make a copy of it because it's the same for everybody, and we don't need to kill 110 pieces of paper or so forth for the same thing. But it will be on Moodle for you to make comparisons for your IR table as far as what your standard or literature information is. It's going to be what is posted on Moodle. Okay? And there'll be a couple around in the labs as well. Alrighty, questions you guys have? Okay.